Hello everyone. Today let's solve the problem number 3 to 7, count of range sum. So what the question states here, we are given an integer array nums. You can clearly see here they have given an integer array nums, right? And two integers lower and upper. You can clearly see here, and we have been given two integers lower and upper. We need to find the number of subarrays I comma j. Means we have to find the number of subarrays where the sum of elements in the subarray lies in the range lower and upper. In this case, they have given the nums array of elements consists of -2, 5 and -1. So lower and upper they have given -2 and +2. The sum of all the subarrays for -2, 5 and -1 should lie between -2 and it has to lie between -2 and +2. So we are not calculating the subarray here. We have to first identify the subarrays of the elements -2, 5 and -1. Then we have to calculate the sum of all the subarrays that lies between -2 and +2. That's what we have to do, right? The sum of elements in the subarray from index I to j is called the range sum. That's what they have given here. So the sum of elements in the subarray from index I to j is called range sum. So this will be the range sum basically, -2, -1 and 2. Here, answer how we got the output 3 here, we are displaying the length of the this one, subarray sum. So the three subarrays that lies between the three subarray sum that lies between -2 to +2, they have given here 0, 0, 2, 2 and this one 0, 2. This is subarray sum, and the respective sums they have given here -2, -1 and 2. So this is the sum, these three, right? The sum of the subarrays that lies between -2 and +2 are -2, -1 and 2. So we have to display the length as output. Means here 1, 2, 3, one index this is, right? This is one index. So 1, 2, 3. The length we have to, this one, what do we call? The length we have to display as the output, or we have to return the length of the sum of the subarrays, number of subarrays, right? As output. So 3 we got here. Same goes with output 2 as well here, example 2 as well here. We have only one element. So the range they have given here is lower 0 and upper 0. It has to lie between 0 and 0. Only one element, that is 0, lies between the this one, lower and upper. We can say this by looking at the example itself, right? Only one element. So we have to here return the length of the sum of the subarray that lies between 0 to 0. That is 1. Nothing but the element 0 or the subarray 0, right? So subarray 0, 0. So I hope the question is completely clear. Let's discuss the approach followed by edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. This is very simple. I'll tell you one thing. So here what we will do, then let's discuss the approach first. First, what we will do here means we will identify all the subarrays for this one, nums array. So first what we'll do, first step is we will identify all the subarrays for the nums array. After identifying all the subarrays, what we'll do, we will calculate the prefix sum for all the subarrays of the elements this one, -2, 5 and -1. After calculating the prefix sum, we have the formula for calculating the prefix sum. Also we have the formula for calculating the, so this one, after calculating the prefix sum, we have identified the subarrays and we have calculated the prefix sum for it, right? So after calculating the prefix sum, we have the formula for calculating the this one, sum of the subarrays, right? Sum of the subarrays that lies between -2 to +2. So we will calculate the subarray sum for all the elements, for all the subarrays for these elements. So whichever subarray that lies between this one, -2 to +2, we will identify there itself. Finally, we will return the sum. These are the 3 steps that we will be doing. Only 3 steps. This will be very easy. So let's start the approach. Let's start with the approach. So here we'll discuss the approach step by step. First thing is we are going with the, so I have considered the first example that they have given in the question. Same example that I have considered. So first thing we have to keep in mind here is we are going with the binary index tree or the Fenwick tree to solve this problem. So we will be making use of the BIT or the Fenwick tree to solve this problem. Just keep this in mind. The only disadvantage of using the binary tree, binary index tree is, so we have to build this one from scratch, right? So that is the only disadvantage. Apart from that, it is very easy to understand. So let's make use of binary index tree or the Fenwick tree to solve the problem, right? So the first example that they have mentioned in the question, that itself I have considered here. The first step, what we have to do here, we have to find the number of subarrays whose sum lies between -2 to +2, because lower they have given -2 and upper they have given this one +2, right? So we have to calculate the number of subarrays whose sum lies in the range -2 to +2. First step will be going with here as we will be computing the prefix sum array. As I have said, we will be computing the prefix sum array for this one, for the nums, this one, right? We will be computing the prefix sum array. So we'll be calculating the prefix sum array as I have said. Indexing starts from 0. This we have to keep in mind. Indexing starts from 0. 0, 1, 2 I'll give. Why? We are considering this one, right? 2, 5 and -1 we need to consider. First subarray will go with -2 here, right? -2, 5 and -1 we have -2. So sum, this one prefix sum, how we will calculate? This will be 0 plus plus of -2, because we don't have any prefix for this. We will be considering 0. 0 plus -2 will be here in this case -2. The sum is -2 in this case. So next subarray we will consider 2 elements in this case. Which one? -2 and -5. This 2 we will be considering, right? -2 and -5 we will be considering. So here this will be -2 and -5. We will be calculating the prefix sum. In this case, prefix sum here we already have -2, the previous one, and plus of 5 we are considering, right here. Plus of -5 or 5. Just give me a second here. So we have +5 here. Sorry, not -5 in this case. So this has to be 5. Sorry, just give me a second here. So this has to be just 5, not the -5. Plus of 5. So this one I'll just give here 5. This one will be -2 plus 5 will be 3 in this case, right? So the sum will be 3 in this case. The last one we have to consider here all the 3 elements, -2, -5, -2, 5 and -1. So here let me consider -2, 5 and -1 here. So here this will be 3 plus this one. We have to go with -1, right? So -2, -3, this one. Just give me a second here. Oh, -1 we are considering here, right? So this one, 3 plus of -1. 3 minus 1 is nothing but 2 here. So here the answer is 2. So -2, 3 and 2 we got here, sum, right? So we are calculating the prefix sum array here. This will be -2, 3 and 2. So our prefix sum array here will be, so yeah, our prefix sum array here will be 0, -2, 3 and 2. This will be our prefix sum array. So how we got this one? From the previous step. So I'll just come here. -2, 3 and 2. Initially it was 0. 0, -2, 3 and 2 is our prefix sum array. I hope this is completely clear. So why we will be making use of the prefix sum here? Because the sum of any subarray, nums of ij, can be found using the formula S of ij, prefix of j plus 1 minus prefix of I. This formula we have to keep in mind. The sum of any subarray, that's how we calculated basically. Here, prefix array. That's how we calculated. The previous one plus the subarray that we considered, -2 initially, next we considered +5, and next we considered -1. So the sum we got here is -2, 3, and this one +2, right? So here the sum of any subarray nums of ij can be found using the formula S of ij equals prefix of j plus 1 minus prefix of I. This one we know now, right? So the prefix sum array that we got here is 0, -2, 3, and 2. So this was the first step. Next, let's move to the second step. Let's move on with the second step. Let's identify all the possible subarrays. So let's identify all the subarrays for this one, for the nums array, right? Let's identify all the subarrays for this array. So for the elements that is present in this array, right? Let's identify all the possible. So let's start identifying all the possible subarrays. Here we have the array here. Let me write this one, 2, 5, and -1, right? In the question nums array they have given here. For nums 2, 5, -1, there are 3 elements. So we consider I, j. So there are 3 elements. So we will consider I, j pairs. So we will be starting with I equals 0. When I equals 0, here you can clearly see 0, 0, 0, 1, 0, 2. Why? Because we have 3 elements. The indexing starts from 0. So we are going with 0, 1, and 2 here. So I hope this is clear. For nums -2, 5, -1, there are 3 elements. So we consider I, j points. So we will be considering I, j points. Only zeros. This, if we consider this one as x and y, for x we will be considering 0 because we have to start from I equals 0. Here I equals 2, we will be starting from 2. For I equals 1, we will be starting from 1. I hope this is clear. For y we are considering 0, 1, and 2 here because we have 3 elements here, 0, 1, and 2. Indexing starts from 0. So 0, 1, and 2. We have 3 elements. So we are going with 0, 1, and 2 initially, right? So here for this one, we'll be going with -2. For this one, this will be -2 and -5. And this one, it will be -2. Sorry, this is not -5. I get confused. I'm getting confused. This is only 5. Sorry. 2, 5, and -1, right? For 1, 1 and 1, 2, this is, we will ignore the 0th one, means we will ignore this one, -2 entirely for this one. When we started when we started I equals 1. So we will go with initially 5. Yeah, this will be 5, -1. I hope this is clear. Next thing, when we started 2, we will ignore -2 and -5 here. We will consider only -1, right? At 2, 2. So this will be only -1. I hope this is completely clear. So I hope this is clear, the step of identifying all the possible subarrays, right? I hope this is clear. So again, I am telling why we are considering 3 elements here. I equals 0, I equals 1, I equals 2 means we are having the length here 3. We are having 3 elements within the array, 0, 1, 2. Indexing starts from 0, 0, 1, 2. We are having 3 elements and we are considering the points I, j here, right? So subarrays here, 0, 0, 0, 1, 0, 2, 1, 1, 1, 2, and 2, 2. I hope this is clear. This was the next step. So let's come to the main step, step 2. We have to find all the valid subarrays with the all the valid subarrays whose sum basically falls between -2 and +2. That's what they have asked in the question, right? Whose sum falls between -2 to +2. Lower bound they have given this one, -2, and lower they have given -2, and upper they have given +2 here. So subarray, we have already got the subarray here. This one, 0, 0, 0, 1, 0, 2, 1, 1, 1, 2, 1, 2, 2. How we considered this one? So from this one, identifying all the subarrays. This one, 0, 0, 0, 1, 0, 2, 1, 1, 1, 2, and 2, 2. I hope this is completely clear, right? Formula, we already have this one formula. Prefix of 1 minus prefix of 0. So the previous prefix we are going with every time. We already calculated the prefix sum for this one 0, 0, 0, 1 and 0, 2 if you see here. So we already have calculated. Just for the example sake, I have already shown this one. Just give me a second here. This one -2, 3 and 2 should be the answer for this one, right? So I would have skipped this step, but you wouldn't have understood while we have calculated this one directly. If I would have went with the this step directly, you wouldn't have understood how we would have calculated the prefix sum. That is the reason I have just calculated for the understanding purpose. Here we have calculated the prefix sum for the three elements right here, -2 and 3 and 2. We can write this one directly. Still, I'll show the calculation for this one. Here this one will be -2, 3 and 2. We went with 0, 0, 0, 1 and 0, 2 right here for this one, first three. So this one 0, 0, 0, 1 and 0, 2 here. For next, let's go with the 1, 1. Here, let's go with the numerical calculation. Same thing, -2, -0 here. This one will be 3 minus 0. This one will be 2 minus 0 in this case, right? So this one, for this one 1, 1, it is prefix 2 minus prefix 1. P of 1 minus P of 0 is nothing but prefix of 1 minus prefix of 0. Index, right? Prefix of 1 minus prefix of 0. Prefix of 2 minus prefix of 0. This one. Same goes with the other, this one as well. Other rows as well. So this one will be 2 minus 0. This we know how we calculated here. -2 minus this one plus 3 and plus 2 how we got. Next, we'll be going with for 1, 1 prefix 2 minus prefix 1. Nothing but 3 minus of -2. You can calculate in the similar way. Here, this one will be 2 minus of -2, right? I hope this is clear. The final step is 2 minus 3 here. In this case, we will get 5, 4 and -1. So I hope this is clear, right? How we got this one. We are doing prefix of 2 minus prefix of 1, prefix of 3 minus prefix of 1, prefix of 3 minus prefix of 2. 3 minus of -2, 3 plus 2, 5, 2 plus 2, 4, and finally 2 minus 3 is -1. So what are the valid subarrays here? We have to consider only the subarrays whose sum lies between -2 and +2. That's what they have asked in the question, right? So this one here. This one we have to consider only the sum of the subarrays whose range falls between -2 to +2. That the only those we need to consider, and finally we have to return the length of it, right? Length of it as output. So I'll just come here. In this case, -2, this one lies between -2 to +2. Yes, this one lies, right? So 3, it doesn't 3 doesn't lie between -2 to +2, right? No. 2, yeah, 2 lies between -2 to +2. So we'll be giving S here. So this is fine. 5 doesn't lie. So 4 also doesn't lie here. -1, yes, -1 lies between -2 to +2 here. So we'll be considering this one. So we have 3 subarrays whose sum lies between this one -2 to +2. That is nothing but one is 0, 0, and another one is this one 0, 2, and the third one is 2, 2. This one 0, 0, 0, 2 and 2, 2. So just give me a second here. Let me write here 0, 0, and the second one was this one, right? 0, 2, and third one is 2, 2. These three we have to consider 0, 0, 0, 2 and 2, 2. 0, 2 and 2, 2. This is the subarray. What is the sum here? What are the sums here? This one -2, +2 and -1. -2, plus 2 plus 2 I don't have to write in this way, man. I'll just write plus 2 and minus 1. So finally we have to return the count of the subarray sum that lies between minus 2 to plus 2, right? So here count is nothing but the length here. 1, 2, 3 we have. So we will return 3 in this case. This will be the final output. I hope the approach is completely clear. These are the steps that we need to follow. First, what we did, we went with the we discussed about using the binary index tree or the this one Fenwick tree. First step was we have to find the number of subarrays whose sum lies in the range this one minus 2 to plus 2. Just for the example sake, we computed prefix sum array, right? So first we now have the idea of computing or calculating the prefix sum array. Then we discussed about why we made use of the prefix sums. So why we made use of the prefix sums and how it was helpful. Third one is we went with identifying all the subarrays, right? So we went with identifying all the subarrays. And fourth one, we had the formula to calculate this one, the sum of the subarrays that lies between the particular range, in this case minus 2 to plus 2. And finally we returned the count of it. We got all the this one subarray sum which lies between minus 2 to plus 2 here. Finally we are returning the sum of it over here. I hope this is completely clear, right? So next let's discuss the edge cases. Before discussing the edge cases, I would like to tell you there are only two steps, basically two important steps here. First thing is we should be knowing how to calculate the prefix sum, right? Three steps, sorry. We should be knowing how to calculate the prefix sum. After calculating the prefix sum, we have to identify all the subarrays, and then finally the third step is here. We have the formula to find the valid subarrays within the particular range that they have given. That's it. Only three steps, right? So finally we will return the count of the subarray sum which lies in the range between minus 2 to plus 2 in our case, for the first example that we have considered in the question. So next let's discuss the edge cases one by one. I hope the approach is completely clear. Let's discuss edge cases. So first edge case we'll be considering for a single element within a range. So nums 0, lower 0, upper 0. Output will be 1 in this case. The second example they have given in the question. The same thing I have considered here. So the output will be 1 here. Why the output here is 1? Because the only subarray of 0, this one, the only subarray of 0 has a sum of 0 which is within 0, 0 will be 0, right? This one. So the output here is 1. The only subarray of 0 has a sum of 0 which is within 0, 0, right? So the output will be 1 here in this case. The second edge case is for the all elements out of range here. So 10, 20, 30 we have given. So lower we have considered minus 5 and upper we have considered plus 5 here. So the output will be 0 here. Why the output will be 0 here? Because no subarray sum falls within 5, 5. So the output will be 0 here. No subarray this one sum falls within minus 5, 5. You can just, if you want to try it out why we got output 0, you can just follow the same steps that I had showed during the approach, the first example that we considered from the question. You can just follow the same steps. So the output you will get here is 0 in this case. So this is for the condition all the elements out of range. So let's move on with the third edge case here. All the subarrays are valid. When I say all the subarrays valid, so we are going with the input nums array 1, 1, 1 I have considered, lower 1 and upper 3. Output will be 6 in this case. Why the output here is 6? Every possible subarray sum 1, 2, 3 is within 1, 3. So all the 6 subarrays are valid here, right? Every possible subarray sum 1, 2, 3 is within 1 to 3, right? So here lower we have considered 1 and upper we have considered 3. So every possible subarray sum 1, 2, 3 is within 1, 3. So all the 6 subarrays are valid here. So if you want all the steps to be known, then you have to follow the steps that I showed for this one. Example 1 during the approach. The same steps you have to follow. The fourth edge case that we will be going with here is this one, large negative integer. So output here will be 2 in this case. We have considered this one here, minus 1 lakh to minus 5 lakh. Lower I have considered minus 2 lakh and upper is minus 10,000 here. So the output will be 2 because only here 0, 0 and this one 0, 1 subarrays have sums within the range minus 2 lakh to minus 10,000 here. In this case only the subarray sum subarrays 0, 0 with particular sum and 0, 1 subarray with particular sum will be within the range minus 2 lakh to minus 10,000, right? And then the fifth edge case here is, just give me a second, large array size. So here we have considered 1, minus 1 into 5,000. You can clearly see into 5,000. Lower minus 1, upper plus 1 I have considered here, right? So the output here will be 1 lakh. So yeah, this is fine. So the output here will be 1 lakh. So alternating pattern ensures every adjacent pair 1, minus 1 forms a valid subarray sum within minus 1 to plus 1. So this is for the condition large array size. These are the 5 edge cases that we need to consider. So what was the first edge case here? The first edge case we considered for single element within range. The second edge case we considered for all elements out of range. The third edge case we considered for all the subarrays are valid. The fourth edge case we considered for large negative numbers. And the fifth edge case that we considered for was this one, large array size. I hope all the edge cases are clear along with the approach that we discussed. Now let's start writing the code. So let's start writing the code. So in the approach we saw we have to calculate the prefix sum as well as we need the count of the subarrays whose sum lies between this one particular range they have given, right? So for the prefix I'll just initialize prefix to 0 and count, let me initialize this one to 0 as well, right? So the next step is we will be making use of the set to store the unique prefix sum for coordinate compression. So here in this case I'll just give let vals equals new set this one 0. This is fine. We are making use of the set to store the Unix prefix sums for the coordinate compression, right? So the next step here is we need to store the modified prefix sum for mapping. So here this is fine. So previously here in the line number 4, this sums, what it does here, the sums variable, it stores the modified prefix sums for mapping, right? Let's carry on with the step 1. So first, as we had seen in the approach, we have to compute the prefix sums and generate values for the coordinate compression, right? So how can we articulate that one in the form of code? I'll just give here for let num of nums here. Is this fine? Prefix plus num, right? I hope this is clear. Then finally what we will do, we will add prefix minus lower and prefix minus upper minus 1. So for adding I'll just make use of the push here. So what are the things that I'll add here? This one, prefix minus lower, and another one is prefix minus upper minus 1, right? We are just computing the prefix sums and generating values for the coordinate compression. we know how to compute the prefix. We saw that one in the approach. Previous one minus the number that we are considering in the array, right? So that's what we are writing here. Prefix minus or prefix minus or minus 1. Prefix equals prefix plus num. So we are just making use of the iteration here. That's it. So the step 2 what we saw there, coordinate compression, right? So we have to sort and map the unique prefix sums to indices. That's what we need to do. Again, I'm telling, this is the step 2 what we are going here with this one, coordinate compression. Nothing but the coordinate compression. Nothing but we are sorting and mapping unique prefix sums to indices. So we have to sort and map the unique prefix sums to indices, right? Then first let's see the coordinate compression. So here let sorted I'll give here. I'll just make use of the spread operator for the values and sums here. This is fine. We have to sort here in the ascending order. So I'll just give here A minus B. This is fine. So first what we have done, we sorted. Now we have to map the unique prefix sums to the indices. Let's make use of the hash map here. So I'll just give here let map equals new map. What we have to map? We have to map the unique prefix sums to indices, right? So I'll just make use of the sorted values, sorted dot map here. Let me consider two variables, anything. In my case, I'll just consider b comma I. This will be b comma I plus 1. I hope this is clear, right? So this step, I hope this is completely clear. Next step, let's initialize the binary index tree or Fenwick tree with the compressed size. So for this, we have to build the binary index tree. So what is here? This one has to be mapped. Sorry, this is fine. So let's initialize this one and let's build the binary index tree or the Fenwick tree. So we are initializing binary index tree or the Fenwick tree with compressed size. So I'll just give here binary index tree short form. I'll just give here BIT, new BIT. So sorry. So we have to build the BIT as well, right? This will be length of the sorted. Sorted is the variable that we have used here. This one we are making use of, right? So here we are just initializing BIT with compressed size. Let's build BIT quickly here or the binary index tree quickly here, right? So let me make use of the class here, BIT. So initially we have to initialize. For initialization, I'll just make use of the constructor. Let me pass the parameter size here very quickly. So we have to initialize the size because we have to store the size of the binary index tree or the Fenwick tree initially. So for that, I'll just consider size and let me give a size here. Let me initialize size. This dot size to size. So also we have to consider the BIT array as well, right? So we have to initialize the BIT array with zeros initially. So I'll just consider here this dot tree, this one. Let me make use of unsigned 32-bit integer array. So I'll just give here uint 32 array of size plus 1. I hope this is clear. The next step, this is the initialization part. We are going with the two functions. One is update and one is query. Update because we have to increment the frequency count at index I because we have to move to the next index, right? So we have to increment the frequency count at index I, right? Every time. So next, why we are making use of the query function? We have to compute the cumulative sum up to the index I in binary index tree. So these two steps we need to keep in mind. First one, update and query function. We'll be making use of update and query function. We'll be building update and query. So why update function? Because we have to increment the frequency count at index I. And why query? Because we have to compute the cumulative sum up to index I in the binary index tree or Fenwick tree. So I'll just come here. Let me give update A comma B. This is fine. So what it does here, as I have said, we have to increment the frequency count at index I. So for that, I'll just make use of the simple for loop here. I less than or equal to this dot size I equals I plus I and I. This is fine. Finally, this dot tree. So we have to increment this one frequency count, right? So this dot tree of I iterated value of the tree plus plus. We are just incrementing. This is it for the update. Let's go with the query function. So let me pass the parameter I here, right? So I hope this is clear. Let's initialize the sum to 0 initially. So here, as I have said, we have to compute the cumulative sum up to index I, right? We saw step by step the calculation part. We saw step by step, nothing but when I say cumulative sum up to index I means for each index or for each subarray we considered, we went with the prefix sum. We calculated the prefix sum for it, right? We have calculated the prefix sum. Finally, we have to calculate within the sum within the particular range that they have given. That we will be doing in the varying step. Nothing but we will be computing the cumulative sum up to index I in the binary index tree. I just make use of the simple for loop here. I greater than 0. I equals I minus and this one minus I. I hope this is clear. Sum, let me assign the sum to iterated value of the tree. Sum equals sum plus tree, right? So this keyword we have to use here, iterated value of the tree. I hope this is clear. Finally, we need the sum, right? At every step, we need sum of the particular subarray. So we will return sum in this case. I hope this is completely clear. This is it for the BIT. So we have successfully built the binary index tree here. Let's make use of the functions, update and query functions within the main function, right? So here we have already initialized the BIT or the binary index tree with compressed size. You can clearly see in the line number 32. So let's move on with the next step. Nothing but let's iterate through the array, maintaining the prefix sums. We have to maintain the prefix sums. That was step 1, right? Let's iterate through the array, maintaining the prefix sums and counting valid subarrays. So for that one, I'll just make use of the simple for loop here. Let num of nums, this is fine. This one will be prefix equals prefix plus num. Why we have made use of prefix equals prefix plus num? Yeah, because we have to update the prefix sum every step. That also we saw during the calculation of the prefix sum. Initially in the step 1, if you remember in the approach, we were updating the prefix sum every step for the subarray. When we considered -2, when we considered -2 and 5, when we considered -2, 5 and 1, for every step we have to update the prefix sum, if you remember. So in this case, we have to update the prefix sum. That is the reason I'm considering prefix equals prefix plus num. Next step is we have to count the number of valid subarrays ending at the particular index, right? Ending at this index, we can say, or ending at the particular index. So how can I articulate that one in the form of code? I'll just give here count equals count plus bit dot query b. We'll be making use of the query here, this one. So let me copy this one here, dot query. To get the value, I'll be going with the get. So map dot get of prefix minus lower. This is fine. Minus again bit dot query map dot get of prefix minus upper minus 1. So I hope this is clear. We are just counting the number of valid subarrays that is ending at this index, right? So the next step here is what we have to do. We have to insert the current prefix sum into the binary index tree for the future queries as well. For that one, I'll be making use of the update here. Let me copy this one. So what we are doing here, again I'm telling, we have to in the previous step, or in the line number 37, if you are looking at line number 37, we are counting the number of valid subarrays that is ending at the particular index. Next, we have to insert the current prefix sum into the binary index tree. Every time we have to insert the current prefix sum into the binary index tree for the future queries, right? How we calculated prefix sum? First, minus 2 plus 0. Initially it was 0, minus 2 plus 0. We have given minus 2. For the next one, we have to store the current prefix sum, right? So next we had minus 2 comma minus 5. So the previous one was minus 2. And we were considering minus 2 plus of minus 5. So we have to store the current prefix sum into the binary index tree for the future queries as well. So how can I articulate that one in the form of code? So I can just write here bit dot. For that one, I'll be making use of the update here. Map dot get of prefix here. This is fine. Prefix minus 1. Prefix comma 1. Initially, 1, right? So 1 indexed. So 1. Let's consider 1 here. Finally, here what we will do? We will return the count. Nothing but we have to return the total count of valid range sum. After this one, calculating every sum, all the sum. So we have to first we have to calculate the sum, and we have to identify the sum that lies between particular range, right? So for that one, lies between particular range, and we have to return the count of it, count of the sum that lies between particular range. For that one, we have to just give here return count in this case. So let me hit the run button now. So here in the line number 30, let's go with the this one. This has to be capital M. So here it is showing wrong answer. Let's see what I have done wrong. So what mistake I have done here is in the update function. Here what we are doing in the update, we are increment the frequency count at the index I, right? So here this has to be I plus I and between minus I. Negative also we have to consider, negative value also we have to consider index. So this is one thing. And one more thing here, just give me a second. Here in the line number 32, you can clearly see here we have initialized the binary index tree with a compressed size. So next step is we have to insert the partial prefix sum, right? When I say partial, not the partial prefix sum, we have to insert the initial prefix sum 0 at bit. Initial prefix sum we saw during the prefix sum calculation during the approach. Initially we considered 0, right? The first one was 0, then minus 2, then we got two more values when we considered the elements, this one minus 2, 5 and minus 1. So we have to insert initial prefix sum 0 into the bit first. So let me give here prefix equals 0, and let's make use of the here update function. So map dot get value, we have to get initially 0. So I'll be making use of the get property of the hash map. So let me give here 1, right? So we are just inserting the initial prefix sum 0 into the bit here in this step. So let me format this one again and let me hit the run button. So you can clearly see now the sample test cases are getting passed, means we can hit the submit button. Let's hit the submit button. So you can clearly see all the test cases are getting passed here. So the code that we have written works completely correct, right? Let's quickly discuss the complexities of the code that we have written. So the approach that we went with here is Fenwick tree or the binary index tree with the coordinate compression. We know this one. So what will be the overall time complexity here? Overall time complexity would be big O of n log n. Why it is here big of n log n? Because we are making use of the sorting. Also, we are going with the BIT operations, this one, update and query. And here we are going with the sorting as well. In the line number 29, you can clearly see sorted, this one, dot sort A, B, ascending order we are sorting here, right? So we are going with the sorting as well as the BIT operations. Here you can clearly see one is update and query. Mainly sorting plays the dominant factor here, though. So the overall time complexity would be big of n log n. So what would be the overall space complexity here? The overall space complexity would be big of n. So why it is big of n here? Because we are storing the prefix sums and BIT. So if you remember in the approach, during the approach, so first we went with the prefix sum calculation, and then also binary indexed tree, we are making use of function and update here in the code, right? So we are storing the prefix sums initially and also the BIT. So this one, BIT and also the prefix sum here. So overall space complexity would be in this case big of n. I hope this is clear. So overall time complexity would be big of an n log n because the sorting plays the dominant factor here, and the overall space complexity would be big of n, right? I hope the solution that we have written is completely clear. For now, this is it. Thanks for watching, guys.